Hello. Good morning to everybody. Now this is PG second year functional analysis, 6th paper. Now we will continue here. Already in the previous class, we have explained John lemma, and before that, what is the partial ordered set and example with example also, and at the same time, what is the John lemma's concept. Now once again, just you have to see here, John lemma statement is, if X is a partially ordered set in which every chain or totally ordered subset has an upper bound, then X contains a maximal element. Students, listen carefully here. John lemma already discussed in the previous class here. Okay. Now, if capital X is a partially ordered set in which every chain that is also called at the same time totally ordered, okay, totally ordered subset, and every chain or totally ordered subset has an upper bound, and given that partial ordered set, a maximal element is there. Now that is the John lemma statement. In examination, in the final examination, every time asked here, state John lemma and state poset and John lemma with examples. Okay. Now you have to see here Hahn-Banach theorem. This theorem is very important in the final examination, and this theorem is also consist in operator theories here. Okay. Let M and M0 be a linear subspaces of a real normal linear space. Okay. Here M and M0 both are linear subspaces of a real normal linear spaces, and M contains M0. Now both subsets, both linear subspaces is one of the induction principle here. M subset of M0 here. Suppose now connective map is M to R. Now here the mapping is F maps M to R. This is the linear mapping. That linear map approaches to linear subspace of a linear subspace of a real normal linear space. Okay, here the image of the part is a system of real numbers is here. Now that linear map can be extended to M0. Okay. Now here given the functional means that is the linear functional part can be extended. Extended means that is the linearly to M0. If there exists here one of the another map is also linear functional map is also F0 is here. Okay. F0 approaches to F0 defines from M0 to script R. Here M and M0 both are linear subspaces of a real normal linear spaces. Here one of the linear functional is F maps M to R is linear, and the extended map is also F0 is also a linear. Now here hence the relation is small m belongs to capital M0. Small m belongs to capital M, and that element is also same linear element is also consisting of M0 is here. So F0 M equals to F of M. Now both linear functionals with respect to M both are equal. So that's why here M and M0 both are linear subspaces of a real normal linear space. Okay. Here M contains M0. So here the linear functional is, that is the statement of here. Okay. Here the definition of extended part is also here. F maps M to R, and F0 defines from M0 to R is also a linear. Hence the relation is F0 of M equals to small f of M. So both linear functions are equal through the linear subspaces of a real normal linear space. Okay, students. Now let us see here. Another lemma is also here. Another lemma. Now this lemma is also consisting here. This lemma completely depends upon the Hahn-Banach theorem, and without lemma, now we can't define the Hahn-Banach theorem. Direct statement and proof is here. Okay, Hahn-Banach Hahn is one of the mathematician, and Banach is also another mathematician. But both concepts are same here. So that's why here the extended linear functional is also both here the different linear subspaces, and it depends of the depends upon the mapping, linear functional mapping. Here, f naught of m equals to small f of m. And according to this lemma, just we will see here, lemma students, listen carefully. This theorem is very important. Sometimes state and prove Horn-Banach theorem. If not, now this lemma is must and should be given in the final examination. There is no doubt. Okay. Here lemma is, let capital M be a linear subspaces of a real normal linear space. Now, and before the definition, and then the continue of this lemma, f be a real valued continuous function, a linear functional on capital M. But x naught is not a vector of capital M. X naught does not belongs to M. But here x naught is not a vector in capital M, and M naught is the linear subspaces generated by x naught. Okay, and capital M, f can be extended to a continuous linear functional f naught on M naught. Okay. Now, this lemma is defined through the extended to a continuous linear functional. So, both functions are both linear functionals, then their norm must be equal. Okay. Norm f naught equals to norm f. Now, this is the theorem. Now, according to this lemma, now that is the simple concept is extended linear functional, and here M naught is the linear subspaces generated by x naught. Generated by x naught means it is consisting of the elements of only x naught be the element generated in M naught. So that's why here M and F can be extended to a continuous linear functional f naught on M naught. F naught on M naught, such that both linear functional, continuous linear functional part, then their norms must be equal. So that's why norm f naught equals to norm f. Now let us see the proof here. Now, first of all, we are taking here x naught is not in M. Suppose x naught is not in M. But here the condition is x naught is not a vector in M, and if M naught is the linear subspace generated by x naught. But here x naught is not in M. But let us, our assumption here, consider the part of capital M naught equal to through the linear subspace x naught generated of x naught plus capital M. It read as generated x naught. Generated means that is the spanned element, spanned vector. Now, here M naught equal to generated of x naught and bracket of x naught and span of x naught. So, this is the spanned element. Span means that is simply generated by vector. Okay. Now, here capital M naught equal to x naught plus capital M. So, every element of M naught can be written uniquely of the form. What is the uniquely of the form? Here, let us see here. Here, small x is consisting of the part of, according to this condition, our assumption, x equal to, now generated element, that is the cyclic part. Cyclic means that is the generated by an element of a group. Okay. Now, that generated element can also be written as A into x naught. Okay, A into x naught plus small m. Here, A being any one of the scalar. Okay, or alpha x naught. Okay, please stay on the line. IVDS. Hello? Class lo unna cheppu parla. Parla cheppu. నేను చెప్తానులే అయితే. ఓకే, అలాగే నేను ఇంత క్లాస్లో ఉన్నాను, అందుకని లిఫ్ట్ చేయలేదు, మళ్ళీ చేశాను, కంగారు పడతామని చేశాను. ఓకే, అలాగే షూర్. హలో. సో here x equal to alpha x naught plus capital M. Here alpha be any real scalar there. Okay, here small m is also belongs to capital M. So define a function f naught on capital M as follows. So f naught of x equal to, students listen carefully, f naught of x equal to f of m plus alpha r naught. Now here f naught of x means applying on both sides, that is the linear functional part, f naught of x equal to f of m plus alpha x naught is here. Here alpha r naught means r naught is a real number, one of the real number. Now here norm f naught equal to norm f, from the definition above the definition, extended linear functional definition. So f naught is linear and bounded, because that is the continuous function is bounded. Now already given the condition is here continuous of the linear functional part. So given the f naught is linear bounded and f naught of m equals to small f of m, and the above, just we have to see the above definition. And according to this, when the norms are equal, then automatically f naught of m equals to f of m, for all small m being the element of capital M. That is the linear subspace element. Okay, we now prove that, or how to prove this one? Norm f naught equals to norm f. Norm f naught equals to norm f. By definition of a norm of a functional, we have norm f naught equals to, what is the norm condition? Supremum of mod f of x. Now, here supremum of, now this can also be written as with respect to of the element is f naught of x. So, now according to the norm definition of a norm of a functional part, norm f naught equal to supremum of mod f of x naught. That is the by the definition of norm of a functional part. Okay. Now, here x being the element of capital M naught. Student, listen carefully. What is the condition of this here? Here, x, the norm of x is less than or equal to 1 is there. So, entire that condition must be exceeds greater than or equal to supremum of mod f naught of x. Here, x belongs to m naught under norm x less than or equal to 1. But here the condition is, now the taking of the element is greater than or equal to, that is the inequality. But here m is less than or equal to m naught here. Now, already m contains m naught. Okay, according to the that one, m contained or equal to m naught, and through this one, entire that value is greater than or equal to supremum of that inequality is greater than or equal to supremum of mod f naught of x. So this value must be equal to supremum of mod f of x. Here x belongs to, students, see here, supremum mod f of x, here x belongs to m naught, norm x less than or equal to 1. So here the condition is f of x equal to f naught of x. So that value is, this value is an equivalent to, this value is an equivalent to, that is norm f. So that is by the definition of norm of f. So norm f equals to supremum mod of fx, and replacing that value is by the definition of norm f is, so supremum mod f of x means norm f is here. So the first condition is verified, norm f less than or equal to norm f naught. So that is the first equation. Now we choose another real constant, that is the r naught, or the assumption of the number r naught here, norm f naught less than or equal to norm f. So that is the a less than or equal to b and b less than or equal to a. And according to this one, our assumption x1 and x2, both elements are belongs to capital M. So f of x2 minus f of x1 equal to f of x2 minus x1. It cannot exceed the absolute of f of x2 minus x1. So this value is equivalent to less than or equal to norm f and norm x2 minus x1 here. So this value, it cannot, that must exceed here. Okay, cannot now less than or equal to norm f into this, this element can also be written as in between x naught. Now norm x2 minus x1 may be written as with respect to the x naught. Adding with x naught, that is norm x1 plus x naught here, and plus norm x2 plus x naught here. Okay. Now, or that is the inequality. So x2 minus x1 may be written as, now norm x1 plus x naught minus x1 plus norm x naught x2 plus x naught here. So x naught adding with in between the norm, we are taking the element is no, that is the norm equal to norm f into norm x1 plus x naught plus, now this is, students, listen carefully. Okay, this is x1 minus x naught, not plus. Please rectify this mistake. Okay, this is x1 minus x naught. So norm f into norm x1 minus x naught plus norm f into x2 plus x naught here. So enter that value and according to the norm f of x1 minus x naught means, so that is minus f of x1, this value minus f of x1, enter this value converting into this side, minus norm f into norm x1 minus x naught. This is minus. Please rectify this mistake. See in your textbook. Okay. Now minus f of x1. Now in the left hand side of the part, f of x2 minus f of x1 equal to norm f into norm x1 minus x naught plus norm f into norm x2 plus x naught here. So that's why minus f of x1 here, and this value converting into this side at left side, and f of x2 converting it at right side of this part. We are taking that both elements are interchanged here. Now minus f of x1 minus norm f into norm x1 minus x0, and again this value less than or equal to norm f into norm x2 plus x0, and plus f of x2 converting into at right side, taking at right side minus f of x2. Say that is the second equation. So from the second equation, that the second equation inequality. So that inequality of the second equation, it holds for all x1, x2 elements being the capital M part is here. Now we are taking on both sides here supremum of the supremum of minus f of x minus norm f into norm x plus x0 less than or equal to infimum of. So that is the second equation inequality here. So here x being the element of capital M, and at the same time supremum of negative equals to negative of the infimum. So that's why we are taking here. So that that value can also be written as so this is the negative of this part. So that's why minus infimum of norm f, because minus is here. So common part is minus is here. So infimum of norm f, norm x minus x0 minus of f of x. Okay. So this value is the supremum of the value. This is the supremum of the value, supremum of minus f of x, because x1, x2 both elements are belongs to capital M. So that's why we are replacing in x1, x2 by we are taking a small x is here. So minus f of x, supremum of minus f of x into my supremum minus f of x minus norm f into x plus x0. Replacing x1, x2 by x is here. So supremum of the negative equals to, that is the negative of the infimum. So that's why supremum of the negative equals to negative of infimum is here. So negative means, that is the minus means less than or equal to infimum of norm f into x1 plus x1 minus x0, and minus f of x is here. Okay, replacing x1 by x is here. Say that is the third equation. So enter the supremum value is small a, and on the right side of the part infimum value is small b is here. Okay. Now say by the inequality third equation. See here third inequality. Now here the condition is a less than or equal to b is here. Okay. Now that is the simple proof. There is no confuse. There is nothing but the confusion here. Okay. Or not be any one of the real number. That real number lies between a and b. So a less than or equal to or less than or not less than or equal to b. Okay. Then it follows a means minus f of x minus norm f into norm x minus x0 less than or equal to or not, and less than or equal to norm f into norm x plus x0 minus f of x. So R naught now minus f of x we are taking now adding with plus f of x. So that is the deleting of the part on both sides. Minus f of x is here. So adding enter that inequality adding with plus f of x. So that's why minus norm f into norm x minus x0. So less than or equal to R naught plus f of x less than or equal to norm f into norm x plus x0. So alpha being the non-zero of the element. So dividing by alpha given in this inequality in the fourth equation. Fourth equation means one of the inequalities here. So that inequality here alpha being the non-zero element means inverse exists. So minus norm f into norm x by alpha plus x0 less than or equal to R naught plus f of x by alpha, and less than or equal to norm f into norm x by alpha plus x0. So enter that value R naught plus. So we are taking at right side of the part R naught plus f of x by alpha less than or equal to norm f into norm x by alpha plus x0. So multiplying with alpha R naught plus f of x less than or equal to norm f into norm x plus alpha x0. So LCM after the LCM of this part we are considered here alpha R naught plus f of x less than or equal to norm f into norm x plus alpha x0. So finally here f naught linear functional part alpha R naught plus f of x means f of x plus alpha r naught. Okay, less than or equal to norm f into x plus alpha x naught. So this is alpha r naught is here. This is r naught. Okay. Now, and another one, if alpha less than 0 and the above the inequality taking it to the left side of this part, minus norm f into norm x by alpha plus x naught less than or equal to r naught plus. Now there are, this is the first part and this is the second part. Now here we are, first of all, we are taking that right side, middle of the part, at right side of the part. So we are getting here f naught of x plus alpha r naught less than or equal to, this is r naught. Okay, please rectify this mistake. This is r naught. Okay. Now another one, taking it, we are taking at left side of this part in the above inequality, minus norm f norm x by alpha plus r naught less than or equal to r naught plus f of x by alpha. So finally, we are multiplying entire that inequality, multiplying with alpha, minus alpha into norm f plus x by alpha. Okay, this is x by alpha minus x naught here. Okay, less than or equal to, greater than or equal to, because at right side of this part. Okay, so alpha less than 0, it follows that minus alpha into norm f norm x by alpha plus x naught greater than or equal to. So this is alpha r naught plus alpha into f of x by alpha. So entire that inequality is multiplying with minus alpha here. So minus of less than or equal to means that is the greater than or equal to part. So we are considered here alpha r naught plus f of x, because we are deleting of the alpha, cancelled by alpha is here. So that is f naught of enter that value is an equivalent to f naught of x alpha x plus alpha r naught. So that is minus alpha into norm f and norm x plus alpha x naught by mod alpha, because alpha being the less than 0. So minus alpha into norm alpha and norm x plus alpha x naught by mod alpha greater than or equal to f naught of x plus alpha x naught. Say this is the, now enter that inequality can also be stated as f naught of x plus alpha x naught less than or equal to norm alpha into norm x plus alpha x naught, because now both are cancelled here. Say this is the sixth equation. So from the fifth and sixth equation, now that is f naught of x plus alpha x naught less than or equal to norm f into norm x plus alpha x naught, for all x being the, x belongs to capital M and alpha being the real number. So we are taking the negative of minus f naught of x plus alpha x naught. Just you have to see here. Step by step, I must explain here. Okay. Minus f naught of x plus alpha x naught equal to f naught of minus x minus alpha x naught. Students, listen carefully. So this value less than or equal to entire that value norm f into norm x minus alpha x naught. So that's why that value in the negative norm of the negative means that is the double mod of the part norm means. So that's why we are taking that value is positive. So norm f into norm of x plus alpha x naught. So finally f naught of x plus alpha x naught less than or equal to norm f into norm x plus alpha x naught. So this value say z is there. X plus alpha x naught is say z. So absolute expression can also be stated as norm f naught of z less than or equal to norm f into norm z. So by the definition of the norm f naught equal to supremum of mod f naught of z. So already here z being the element of capital M. So that is z means alpha x plus alpha x naught. So then their norm less than or equal to unit norm is here, say less than or equal to 1. So entire that inequality cannot exceed supremum of norm f into norm z. Here norm z is less than or equal to 1. So that is the by say seventh equation. So enter this value is equivalent to norm f is there, because norm mod supremum of mod f naught of z stated as f naught of z is replacing of the part, norm f is there. So that's why this value is also say norm is there. So this is the absolute expression. That is not the norm. Okay, this is supremum of mod f into mod z. So mod f of z means mod f into mod z. So this is not norm is here. By the definition of the norm, supremum of mod means that is the norm f. So finally, norm f less than or equal to norm f you are given here. So that is the eighth equation. From first and the eighth equation, norm f equal to norm f naught. Now, this is one of the important theorem. We have proved lemma, the above lemma for only real normal linear space. Okay. At the same time, you must write the replacing by real means complex linear space is also, it also holds good. Okay. Now this can now complex linear space. How to prove the complex linear space? Now here the assumption of the part is f naught by capital F is there. In this lemma, small f naught by in the above lemma can also be written as you are taking here small f naught replacing f naught by capital F. So we are giving the proof of complex linear space. Now this theorem also holds good. Then their norms must be equal. So that is norm capital F equal to norm F is here. Now this theorem is also very important. Now number of times these three theorems, second lemma, third lemma, 6 point, this is in the 6th unit. And according to this one, we will explain the Horn-Banach theorem concept. So here, just have to outline of this lemma is let M be a complex linear subspace of the complex normal linear space. Say that is capital N. And F be the complex valued continuous linear functional on M. So here x naught is not a vector of capital M is here, and capital M naught equal to generated of x naught plus M. Now f can be extended to a complex linear functional on the complex linear space M naught such that norm capital F equal to norm small f. Okay. Now let us see this proof. Here recall every complex linear space is also a real linear space. There is no doubt. Already in the above lemma, we have derived for real linear space of the continuous linear functional part. And both norms are equal, extended linear functional part and your norm f not equal to norm f. Now in the above lemma. Now we will see here, this is the complex linear space is always, it is also a real linear space, and we are taking the continuous linear functional is small f. Okay. Now that is the complex linear functional of the part. Now complex linear space capital M, that is f of x equal to g of x plus I into h of x. Now there is the complex form is here z equal to x plus iy is there. Here z means f of x equal to, and x means now that is x means f of x plus I into h of x. Okay. Now please stay on the line. Hello. Class lo unnana ayipinda cheyamantara. Okay, it's almost done. Okay. Now this is my f of x equals to g of x plus I into h of x. Here small x belongs to capital M. Here g and h both are real linear functional on the real linear space capital M. So that is mod g of x cannot exceed the mod f of x less than or equal to norm f into norm x. Here that function is f is bounded. It follows g is bounded. The function is bounded means given according to the complex form in terms of the functions linear functional part f of x equal to g of x plus I into h of x. So this is the complex form a plus ib or x plus iy, whatever it is. Now we are taking the absolute of g of x. So absolute means mod g of x cannot exceed the mod f of x and less than or equal to mod representation in terms of the norm f into norm x. Here x belongs to M. So given the function is bounded. Now in the examination, particularly real linear space means you must attempt only real, you must answerable only real linear space, and don't write the complex linear space. Okay. Now, exact question is also you must be present here. Now, given the function is bounded, it follows that function g is also bounded. Similarly, h is also bounded. because enter all the functions are continuous linear functional. Already we know that every continuous function is bounded. So that's why given the function is bounded, because this is the absolute function and this is also absolute g of x less than or equal to mod f of x, and again less than or equal to norm f into norm x is here. So all the functions are bounded here because since it is linearly continuous linear function part is here. Now that's why you are taking g and h, both are a real valued continuous linear functional. So because this is the real part and this is the imaginary part. So these two parts are real valued continuous linear functional defined on capital M. So that's why we have f of x equal to g of x plus I into h of x. And again, imaginary of the, you must applying the imaginary. So that is I into f of x equal to I into g of x. I into I is I square. I square means that is the minus h of x is here. So enter the above concept, above complex function is multiplying with I into f of x equal to I g of x minus I into I is I square. I square means that is the minus 1. So that's why minus h of x is here. So g of ix. So this is I into g of x means g of ix plus I into h of ix, replacing x by ix. So g of ix plus I into h of ix. So in the above inequality, we are replacing x by ix, g of ix plus I into h of ix equal to f of ix is here. One time is multiplying with I, and second one, because since a function is linear, it follows, and again here replacing x by ix, f of ix equal to g of ix plus I into h of ix. So f of ix means that is, it can also be written as I into f of x. Already we know that I into f of x means I g of x minus h of x. So both are equal here. So h of x equal to, what is the value of h of x? Here h of x equal to g of minus g of ix. So comparing real parts and real parts on both sides. This is the real part. And here the real part is here. So h of x equal to minus g of ix is here. So comparing on both sides by real parts on both sides, comparing it with the real parts on both sides. So that's why this is the real part. And here the left hand side of the real part is g of ix. So minus h of x equal to g of ix, and at the same time h of x equal to minus g of ix. Okay, therefore f can be represented as f of x equal to g of x minus, replacing that value. Okay, f of x equal to g of x minus I into g of x. Okay, I into g of ix. Okay, now g of x is a real valued continuous linear functional. That's why norm g equal to norm capital G is here. So the G, capital G is also linear functional on M naught. So that's why here define the functional capital F of x on capital M naught. F of x equal to g of x minus I into g of ix. Here x belongs to capital M naught. So capital F of x is a complex linear functional on M naught, and f is the extension of small f on M naught. Here capital F means that is the one of the extension of the small f function on capital M naught here. So f is bounded and norm f equal to norm capital F equal to norm small f. So here x be an arbitrary element of capital M naught. That's why capital F of x equal to that is the arbitrary element, through the arbitrary element small r into e power ix. Okay, that is the, in the terms you are taking the polar coordinates, that is the circulation of this part. Here r is greater than or equal to 0 and capital A is real. So r equal to e power minus I into capital A of f of x. So that is capital F into e power minus IA of x. Okay. Now here the f is complex linear. So that's why just you have to see here. Capital F of e power minus IA into x is real. So f into e power minus IA of x equal to, that is the g is the extension of this part. Capital G of e power minus IA of x, both are equal here. So you must applying here on both sides absolute. You are taking the on both sides absolute part. So that is absolute of f of e power minus ia of x equal to mod g into e power minus ia of x. So enter that value cannot exceed the less than or equal to norm g into norm e power minus ia of x. So that is norm g into this value is also norm x. So students, listen carefully. Given the function is bounded and continuous, so that's why norm f, and according to this one, you must applying on the real linear space in the same manner. We must prove it here. It follows that norm f less than or equal to norm small f. And suppose m contained or equal to m naught, it follows that norm small f less than or equal to norm capital F. In the above two inequalities, norm small f equal to norm capital F. That is the proved lemma. Okay. Now, one is the real linear space and second one is the complex linear space, and it depends upon the linear functional, extended linear functional, then their norms must be equal. That is the lemma concept. One is the real normal linear space and second one is the complex normal linear space, and that is the extended linear functional theorems, and that is the above two lemmas. Now, we have referred in the above two lemmas, we must follow the Horn-Banach theorem. Okay. So this is just you have to see here. What is the Horn-Banach theorem? This is the straight theorem, and this theorem completely depends upon the above two concepts, two lemmas. Now, here capital M be a linear subspace of a normal linear space, capital N, and F be a functional defined on capital M. Now, here small f can be extended to a functional f naught. Same, there is no doubt. Here, direct concept is, here we are only capital M be a linear subspace of a normal linear space, capital N. So, f is connecting with the capital M to N. Okay, and here the extended functional part is f naught. Now, f naught is also on the space capital N. That is the image of the part. Image of the normal linear space is capital N. So, f defined from M to N, and f naught is the extended linear functional, M to N is here. So, both norms are equal through the linear functional part. So, that is norm f naught equal to norm f. Now, directly we are taking here, and without m naught, here n replacing m naught by n is here. So, if f maps m to n and f naught is also defined m to n is here. So, f naught is on the space capital N is here. Norm f naught equals to norm f. Now, students, listen carefully. This theorem, a completely Horn-Banach theorem, through the linear functional part is set of all continuous, set of all extension function set is capital B. Script B is here. Script B the set of all extensions of f to functionals G. F2 functionals G with the same norm defined on subspace which contain capital M is here. Now we are taking a different, now we are taking the relation in between the different extra functionals, that is G1 and G2. Okay, G1 is partial, G1 is the relation of G2. This is the Poset relation. Through the Poset definition, this is the partial order relation. G1 is partial order relation G2. If domain of G1, same, that is also contained in the domain G2. So, G1 of x equal to G2 of x through this relation for partial order relation. It is easy to see that, and that is the set of all extension function set is script B. That is also a partial order set, and through the partial order relation and script CBA chain, any two elements are comparable, so that is called a chain. So, CBA chain in script B. Define a linear functional capital G. The domain of G is the union of the domain of G values. Union of the domain of G values. So, this is also for all small g belongs to script B. So, x is in the domain of capital G. So, that is capital G of x is equal to small g of x. Here, small being the G being the one of the chain is here. And that mapping is also G be the one of the domain. The domain is also consisting of the chain part. So, x is in the domain of G. Since C is a chain, the functional capital G is well defined. Now, we have to see here G belongs to script B. The set of all extension function, we are taking the one of the linear extension function is capital G is here in the set of the linear set of the extended functions. So script G is an upper bound for the chain capital C is here. So suppose the C be the chain. C be the chain here. Okay. So the chain arbitrary, it follows that every chain in B has an upper bound. By John Lemma, that is one of the maximal element is here. So that maximal element is say F naught. Okay. Now every chain must be an upper bound, and by John Lemma's concept, that set is also consisting one of the maximal element. So that is F naught. We now show that F naught is an extension of F to the whole space N. Then that is the proof that the domain of F naught is also a capital N. So capital M naught is the domain of F naught. So finally here M naught equal to N is here. Suppose that is our claim. But here, that is not possible part. Suppose M naught not equal to N, we are taking the X naught being the existence element in capital N is here. So X naught is also consisting of capital M naught. So M dash equals to, that is the generated of the vector, that is M dash equals to generated of X naught plus capital M. It is a linear subspace of N which contains M naught and X naught. Though by the lemma in the real case, that is the second real case of the above lemma and complex case of the above lemma. So that is the just you have to see and refer the above two lemmas. Through those lemmas, F naught can be extended to small f naught dash. So that is the image of the functional linear functional part. So F naught dash. For the F naught dash is also a what is that? This is the script B. Script B means what is the script B? The set of all extensions of the functions. That is the, we are taking another one, F naught dash is also F naught. Okay. So that's why F naught in F naught dash is also belongs to script B. That is the contradiction of the part through the maximality of F naught in script B. So finally, M naught equal to N is here. So that is the simple proof of through the partial order relation. Now under the chain definition, you must define the John Lemma's concept. Horn-Banach theorem is completely depends upon the above two lemmas and including the John Lemma. Now that is our simple proof through this concept. Okay. Now, what are the consequences of Horn-Banach theorem? Now these are consequences. Now students, listen carefully. Now entire this unit is also consisting of a paper is operator theory. Now this theorem is very, very important concept. Each and every one must be repeated in operator theory paper. Okay. Now this this terminology is also referred in operator theory paper. Okay. Please stay on the line. Just you have to see the above two lemmas and Horn-Banach theorem. Please stay on the line. Please stay on the line. Please stay on the line. Students, just you have to refer here. See this consequence. Okay. Please wait for 2 minutes. Please wait. Okay, students. Now see this theorem. Now this theorem is must follows the above Horn-Banach theorem's concept. This is one of the in exam. Suppose in the examination is given state and prove Horn-Banach theorem and write the applications. Okay, and state the Horn-Banach theorem and write the consequences of or applications of Horn-Banach theorem. Okay, now here the only statement only is enough, but along with proof is also must necessary here. Let n be a normal linear space and x naught be a non-zero vector. X naught be a non-zero vector in capital N. Then there exists a functional f belongs to n naught such that f of x naught equal to norm x naught and norm f equal to 1 is here. Now let us just have to see this proof here. Okay, one of the sequences f of x naught equal to norm x naught, because here x naught be a non-zero vector, and here in the dual of the linear functional is existence of the linear functional is f. Now that is also considering this function is also considering in dual of the normal linear space, such that through the dual of the linear normal linear space, f of x naught equal to norm x naught and norm f equal to 1. This is the condition. Here f of x naught equal to norm x naught and norm f equal to 1. That is one of the consequence here. First of all, M be the linear subspace generated by the element x naught. So the generated element of the set must be rewritten as M equal to set of. Now we are taking the generated element is the x naught, and we are taking the scalar given the set of the part is set of alpha x naught. So bracket of x naught maybe considered here set of alpha x naught, here alpha being the scalar. All the generated elements, all the spanned elements, you must write the set of the part is you must along with the scalar. So that is set of alpha x naught is here. Okay, capital M is a linear subspace of n, and define a functional on capital M is f of alpha x naught equal to mod alpha into norm x naught. Alpha into norm x naught. We now show that given the function is bounded linear functional on capital M. So that such that norm f equal to 1 is here. What is the linearity? Here Z1 you are taking here Z1, Z2 both are here the linear functional part, linear subspace of the elements. Now Z1 equal to alpha x naught, alpha 1 x naught, and just you are taking different scalars in alpha 1 and alpha 2. Alpha 1 x naught is Z1, alpha 2 x naught is Z2. Now, how to write the linearity condition? Already we know that is f of Z1 plus Z2 equal to f of replacing those values alpha 1 x naught plus alpha 2 x naught, that is alpha 1 plus alpha 2 of x naught. So alpha 1 of norm x naught, alpha 2 of norm x naught here. Okay. Now this is f of Z1 and this is f of Z2. So f of lambda Z1 is f of lambda into Z1 means alpha 1 x naught. So that is lambda alpha 1 into norm x naught. So that is lambda of alpha 1 into norm x naught. So finally lambda into this value is f of Z1 is here. What is the boundedness of this part? mod f of into alpha x naught equal to mod alpha into norm x naught. So norm f can also be written as supremum of absolute of the function. Here norm z is less than or equal to 1. That is the given the condition. So according to this one, z means here alpha x naught, norm alpha x naught less than or equal to 1. Then their supremum of the functional part is, so enter that value is norm alpha x naught. So again they enter this value is then equivalent to 1. Because alpha x naught is less than or equal to 1, then their supremum of the value is also 1 is here. So finally, already just we have observed here, f is the bounded linear functional defined on the subspace capital M, and norm f equal to 1 is here. Okay, students. By Hahn, already we know that Hahn-Banach theorem statement is here. What is that? Norm f naught equals to norm f is okay. Now here the extended linear functional part capital M f defined on the whole space N such that norm f equal to norm f. Norm capital F equal to norm small f. That value is also 1 is here. So with respect to x is f of x equal to small f of x. So here capital F is the dual of the normal linear space. This is the dual of the normal linear space. So f belongs to n star. Okay. So norm capital F equal to 1, and that is f of x naught equal to small f of x naught. So f of x naught is also equivalent to norm x naught is there. So that is the completes of the proof. Okay. Students, listen carefully. Now in the above theorem, okay, just you have to see and refer here. Okay. Remark. From the above theorem, it follows the given x and y both are normal linear space such that x naught equal to y, then there exists f belongs to n star with the property f of x naught equal to f of y. For if x naught equal to y means here x minus y is a non-zero vector. X minus y is a non-zero vector. By theorem, in the above theorem first equation, by the theorem of first equation, there exists f belongs to n star such that norm f equals to 1. So that is f of x minus y equal to norm x minus y. Now this condition is given. Now this is also non-zero of this part through the dual of the linear functional. So f of x not equal to f of y. How to prove the f of x not equal to f of y? Through the norm f naught equals to norm f. Here the condition is f of x naught equal to norm x naught and norm f equal to 1 through the consequence of the Hahn-Banach theorem. And that is the simple concept is, so just you have to see and observe this, one of the remark is here, f of x naught equal to f of y. Through the, that is the extended linear functional in dual of this part. Okay, see the another sequence. Capital M is a closed linear subspace of a normal linear space N, and x naught a vector not in M is there. Then there exists a functional linear functional that is linear functional part is f belongs to N naught is here. F belongs to C here. Such that f of capital M equal to 0 and f of x naught not equal to 0 is there. So consider the quotient space and enter this condition depends upon the quotient space is here. So that quotient mapping is also defined. Now this is one of the sequence capital f of closed linear space of the linear functional is 0 and f of x naught not equal to 0 is here. So J is the defined the map n to n by m. This is the canonical map. So through the canonical map, J of x equal to, so n by m is the quotient space element is coset. So that is x plus capital M. So that is the natural canonical map is J of m equal to 0 and J of x naught equal to x naught plus capital M, replacing x by x naught through the canonical map definition. Okay. Suppose x naught plus m is a non-zero vector in the normal linear space, and through the functional on the quotient space of the dual of the quotient space is also existence of the element is the small f. That is the linear functional. So here norm f equal to 1 and through this one f of x naught plus m equal to norm x naught plus m, because f of x equal to norm x, replacing x by x naught plus m. So that is also norm x naught plus m. We consider the function capital F of x is capital F of x equal to small f of j of x. So capital F of x by replacing x by m is there. Capital F of m equal to, that is the closed linear subspace of the element. So that's why here x belongs to n. So f of capital M equal to small f of j of capital M. That value is also 0. We know that capital F of M equal to 0. So f of x naught equal to small f of j of x naught, replacing x naught by, so through this definition, j of x naught means x naught plus m. So enter that value is also not equal to 0. So because here we now show that capital F is an element of dual of the normal linear space. Now through the linearity condition, first of all, so you must write the linearity and you must express the linearity and boundedness. Okay, linear, already we know, you know that here x and y both elements are normal linear space, and we are taking the alpha beta being the scalars. Okay, now here capital F of alpha x plus beta y equal to small f of j of alpha x plus beta y. Okay, now this can also be written as j of x plus m is also x naught plus m. So that's why we are taking the replay of j of alpha x plus beta y, means this is the x. So j of x naught means x naught plus m. X naught, replacing x naught by alpha x plus beta y plus m. So this is alpha, addition of any two cosets means alpha x plus m plus beta y plus m. That is the addition of cosets. Now next one, here alpha taking it outside, that is the scalar. So f of alpha of x plus m plus beta of y plus m. So alpha of f of x plus m plus beta of f of y plus m. So finally we are getting the values capital F of x, this value is capital F of y. So given the function is linear, through the linear of f of alpha x plus beta y equal to alpha into capital F of x plus beta into capital F of y. Second one, boundedness. Given the function is linear, boundedness means that you must express the absolute expression in between the absolute of capital F of x equal to mod f of x into g of x. So j of x means absolute expression that inequality is less than or equal to norm f into norm j of x. Norm f into norm j into norm x. Already we know that norm j is less than or equal to 1. So that's why this inequality is absolute of f of x equal to norm f into norm x is here. So given the function is bounded, then automatically capital F is also bounded. So f being the dual of the f belongs to n star. Simply in examination, prove that f belongs n star. Prove that f is an element of n star, or f capital F belongs to n star. Simple question is given. That is one of the consequences. Now, you must observe there are two consequences here through from the above theorem, Harmonic theorem. One of the consequences, okay, see this one, f of x naught equal to norm x naught and norm f equals to 1. That is one of the consequence. Okay, and according to this one, capital F of x naught equal to norm x naught, or norm capital F equal to 1. Okay, second one, simply f capital F is an element of n star, means f belongs to n star. That is the second consequence. So third consequence is this theorem is also given in a number of times. Okay, this unit very, very important in the final examination, and very much more utilized, especially Harmonic theorem, much more important concept enter the analyzation branch. So that is especially in functional analysis, either functional analysis or operator theory. Okay, now 6.5.3, this is the third consequence of the Harmonic theorem. So let n be a normal linear space and m be a linear subspace of n. Here x naught be a point of capital N is here, such that D represented as D of x naught and m is there. So D means that is the distance between the x naught and m. So this is the metric condition. So metric is metric with a D referred as D means D of mod x naught minus m. So that mod x naught minus m through the metric, usual metric is infimum of norm x minus x naught. So here x being the element of capital M is positive. So there exists a continuous linear functional f on n That is the echo. Through this condition, continuous linear functional f on n, you must prove that f of x equal to 0. First condition, for all x belongs to m. Second one, f of x not equal to d. And third condition, norm f equal to 1. So this is also very simple concept. Yeah, please, you must refer. This proof is also here in the above two inequalities and the above two consequences of Horn-Banach theorem. It follows that is the simple proof in this. This is also one of the consequence and application. Okay. Now here the usual metric d equals to d be the metric with d. So that is d of x naught and m equal to infimum of norm x minus x naught. Here x belongs to m. And f is the existence of continuous linear functional f on n, f of x equal to 0 for all x belongs to capital M, and f of x naught equal to small d. So norm f equal to 1 is here. Since d is greater than 0, it follows that x naught is not in m. So m naught means that is the generated element. To write generated of m is here. So generated x naught plus m. Now you are taking the element in given in the set, that is alpha x naught plus m. Here small m belongs to capital M. Now you must write the small f of m plus alpha x naught equal to alpha into, so that value is say small d. Enter that value is alpha d. Okay, f is linear on m. If alpha is non-zero, through this condition, given the function is bounded and norm f equal to 1, that is our desired part. Okay, if alpha not equal to 0, norm small m plus alpha x naught. So that is mod alpha into norm m by alpha plus x naught is greater than or equal to mod alpha into d. Okay, so enter the value is an equivalent to d equal to f of x naught minus m less than or equal to norm f into norm x naught minus m. So finally, then their inequality is d cannot exceed the norm f into infimum of norm x naught minus m. So enter that value stated as this value small d into norm f. It follows that norm f is greater than or equal to 1. Finally, f naught of x naught equal to f of x naught equal to d. From the relation, the above relation, norm f naught equal to 1 and f naught of m equal to f of m equal to 0. Okay. Now the enter the unity is also Horn-Banach theorem. Very, very important. First two lemmas, and according to we must derive the part of direct theorem is Horn-Banach theorem, and especially in this unit, how to write the applications of Horn-Banach theorem. Now, after main theorem, Horn-Banach theorem concept, according to the Horn-Banach theorem, you first of all, we have explained the applications of these three applications. Okay, very, very important in the final examination. Okay, don't deviate here. Okay. Now, just you have to see number of times this value is also given. This is one of the problem. Prove that there is a continuous linear functional f on C naught such that f of E1 equal to 3, f of E2 equal to 5. That is a simple concept. Now, through the linear condition is f naught defined capital M to R, f naught of alpha. This is alpha x plus beta y. Here x means replacing alpha E1 plus beta E2. Alpha E1 plus beta E2. So alpha into f naught of E1 plus beta into f naught of E2. So f naught of E1 is 3, f naught of E2 is 5. Replacing of the value is 3 alpha plus 5 beta, given the extended linear functional is linear. So now substituting of the values f naught of E1 and f naught of E2. So you must write the f naught of absolute boundedness of the part mod f naught of alpha E1 plus, this is E1 not E2 is here. Students, listen carefully. This is, please rectify this mistake in the self-assignment questions. Alpha E1 plus beta E2. So this is mod 3 alpha plus 5 beta less than or equal to 3 into mod alpha plus 5 into mod beta. So here those values are equal. In between, that is 3 plus 5, both are scalars. Here that is in the real part. So 3 plus 5 is 8. The maximum of mod alpha and mod beta is here. So enter the maximum of mod alpha and mod beta of the maximum part can also be written as in the norm alpha E1 plus beta E2. So f naught is bounded with norm f naught less than or equal to 8. So by Horn-Banach theorem, f naught can be extended to a continuous linear functional f belongs to C naught. So f of E1 equal to f naught of E1 equal to 3, f of E2 equal to f naught of E2 equal to 5. So this is also important in the examination. Number of times is given in the partial order set of integers under this is the partial order relation. Prove that there is no maximal element. So in the previous paper is also given. This is also that very simple. Z be the set of integers. U be the maximal element in Z. So combine the math through the mathematical induction. U plus 1 is greater than U. Since U is maximal, so U plus 1 is less than or equal to U. So U lies between U plus 1 less than or equal to U, but it is less than U plus 1. That is the contradiction part. So there is no maximal, that set of integers has no maximal element. Okay. By John lemma, there is a maximal linear subspace of C naught not containing a given element x not equal to x equal not equal to 0. This is the exercise problems depends upon the Horn-Banach theorem. Okay. See this one through the John lemma. That is simple expression. Okay. Show by an example that the continuous linear extension generated by this is guaranteed by Horn-Banach theorem need not be unique. Continuous linear extension that is not considered by Horn-Banach theorem need not be unique. This is also one of the problem. Prove that there is a continuous, just you have to explain here. Okay. Another one, here the canonical part is F defined, sigma defined M to N or through the duality. So F defined from M to N and the dual of closed linear subspaces sigma defined from N star to M star. So here the one of the dual of the linear function is say F belongs to N star, sigma of F through this relation, sigma of F equal to, that is the quotient space, that is F by M. Already we have explained in the quotient space. Okay. The restriction of, this is also restriction of N and restriction of M naught. Restriction of M or dual of N and dual of M or restriction of N and restriction of F. M. So the restriction of F to M. That is prove that given the defined the map sigma is onto. That is the simple concept. Okay, students. This is the end of this unit. Very important concept. Don't deviate here. Please stay on the line. Now, after that, Horn-Banach theorem, please see here, open mapping theorem. This theorem is very important in functional analysis paper and operator theory paper, that is paper 11. Now, these theorems are considered Horn-Banach theorem of the concept. Through the Horn-Banach theorem, we must explain, we will explain the open mapping theorem and closed graph theorem. Okay. What is the open mapping theorem? See here. And before that, already we have learned Baire category theorem. Okay. In the real analysis paper. For what is the first category? What is the second category sets? Okay. Now, here just you have to see and refer the Baire category theorem. A subset. What is the first category and second category? So, before that, what is the nowhere dense? A subset of a metric space is said to nowhere dense if its closure has empty interior. Closure of empty interior is called, empty interior of the closure is called nowhere dense. Okay, through the subset of a metric space. So, a subset of a metric space is said to be first category means it can be written as the union of the countable family of nowhere dense means closure of interior, closure of empty interior. Okay, closure of empty interior. So that is called nowhere dense. So that is A closure equal to pi. So that is called nowhere dense. So A means that is the subset of a metric space. So the union of those nowhere dense subsets of the union is called first category. Okay, union of a countable family of nowhere dense sets is called first category. If it is not first category, that is the second category part. So see the Berry category theorem. This theorem is very important in the final examination. Already we have learned in the real analysis paper in the starting part, in the first unit of real analysis. Okay, so once I have to repeat here, what is the Berry category theorem? That is a simple statement. Every complete metric space is of second category. Every complete metric space. What is the complete metric space? Cauchy sequence converges to a point. Okay. Cauchy sequence. Suppose in a metric space, there are two sequences are here. Xn and Xm. That the sequence of the Cauchy sequence means that the distance between Xn and Xm is less than epsilon, or mod Xn minus Xm is less than epsilon. Okay. So here, and before that, mod Xn converges to the Xn and Xm both are converges point is in the same point. So that is the Cauchy sequence. So that when the Cauchy sequence converges point is called complete metric space. Okay. Now every complete metric space is of second category. Now that is the second category means that is the union of the nowhere dense subsets. Union of the countable family of nowhere dense sets is non-empty of the part. Non-empty interior is called, okay, the union of the sequence of its subsets. Then the closure of at least one set in the sequence must have non-empty interior. So you must write the second category definition through the complete metric space. And if not, simple statement is every complete metric space is of second category. That is the statement of Berry category theorem. In examination, state and prove Berry category theorem. Now, number of times asked in real analysis, either real analysis, and the same theorem it follows the functional analysis paper. Now here, A and B, one of the sequence, once I have to repeat here, that sequence of the metric space capital X, here capital X equal to the union of all the representations. Union of all the sequences is called capital X. Here, then the closure of the subsets of the interior is empty. Here, n equal to 1, 2, and so on. So, int of A means the interior of A, interior of the set. So, An is nowhere dense subset of X. Here, if X is, since X is open, so A1 is nowhere dense set. By the above remark is here. So here we find an open sphere S1 of radius less than 1, which is disjoint from A1. The concentric closed sphere is F1, and those whose radius is 1/2 of S1 here. And again, interior of F1 is open. And again, you are taking the A2 is also nowhere dense. Nowhere dense. Since nowhere dense means closure of the subset is empty, interior. Union of the closure is interior, empty interior. So that is called nowhere dense. And again, interior of F1 contains another open sphere is S2, whose radius is less than 1/2. Whose radius is less than, sir, class lo unnanu sir. అక్కర్లేదండి, నేను మళ్ళీ చేస్తానండి, క్లాస్లో ఉన్నాను. అది okay. Now again consider the concentric closed sphere F2 whose radius is 1/2 of S2. Now interior of F2 is open and A3 is nowhere dense. A3 is nowhere dense. So S3 is the another open sphere whose radius is less than 1/2 square means 1/4. It is also disjoint from A3. So containing these properties is we are taking the one of another sequence. Nth sequence is sequence Fn is a closed sets of X. So that is the diameter of sequences is converges to 0. So here D means that is the diameter of Fn. So diameter of the set Fn converges to 0 means we are taking the supremum of the values in the different sequential representation, that is in between A1 and A2. So A1 and A2, this is A2, not E2. A1 and A2, though both are considering in the sequence values, see the different sequences of the values in Fn. So that is capital X is complete because converges to a point is here. So that is the Cauchy sequence is converges to a point. So given the arbitrary set is capital X is complete because here X means what is the X? Explained here. What is the X? That is the metric space. So given the metric space is complete, so complete metric space is of second category. So that's why Bailey category theorem is verified. So arbitrary union is that is the second category means if not first category. If not first category means that is the arbitrary union of Fn is non-empty is here. So the Cantor intersection theorem, arbitrary intersection of Fn is the concentric closed spheres. Here arbitrary intersection of Fn is non-empty. So by Cantor intersection theorem, it follows that at least one arbitrary element is here. Non-empty means. So small x is contained or equal to x. Construction of the Fn values, x is not in any of the sets An. So finally, x is not in arbitrary intersection of the part. So that's why that equals to capital X. That is the contradiction of the theorem. Okay, that's enough. What is the open mapping theorem? See the first lemma. Okay, now before the open mapping theorem, first of all, our claim, first of all, you must know the what is the S of XR. Here the S be the sphere. What is the sphere? A set of points in space which are at a constant distance from the fixed point. Here fixed point is called center. That center is small x. And R be the constant distance. That is called the radius. So sphere represent is S of X and R. Here R be the radius and X be the center. And that is simply denoted as S of XR and SR of X. SR of X means here R be its radius and X be the center. Now you must write the S of X and R or SR of X, base R of X. Okay. And origin, through the origin, center at origin, SR. Simply that is also SR denote the sphere with the origin as center and R as radius. Because SR of 0 or SR of epsilon, because epsilon is greater than 0, SR of S epsilon of X. Okay. Now, according to that condition, you must explain the given this lemma and you first of all briefly you must explain the open mapping theorem. First of all, you must see and verify given this lemma. Let B and B dash be, there are two Banach spaces. Students, listen carefully. There are two Banach spaces and continuous linear transformation is defined from capital T defined B onto B dash. Okay. Now, here the image of the open sphere is SR in B dash. SR in B contains an open sphere SK dash in B dash. So, here center at origin and that origin of the Banach space open sphere is SR. Center at origin of the open sphere is SR in B and SK dash in B dash. Another open sphere. So, SR belongs to B is a subset of open sphere SK dash belongs to B dash. That is the theorem. That is the simple proof. This theorem is very important in the examination and according to just you have to see and verify this lemma. Okay. Because there is no time. This theorem is very important in the final examination. There is no doubt. And through this theorem, how to prove the open mapping theorem? 7.4.2. This theorem is very, very important in functional analysis, open mapping theorem and closed graph theorem. Both theorems are very, very important and especially in the entire analyzation concept, how to prove the open mapping theorem. There are two Banach spaces and a continuous linear transformation is capital T defined from B onto B dash. When the T defined the continuous linear transformation B onto B dash, then the transformation is continuous linear transformation is an open mapping. That is the simple statement. B and B dash, first of all, B and B dash both are two Banach spaces. Okay. And now that transformation is denoted by what is that transformation? Continuous linear transformation. T defined from B onto B dash. That linear transformation is open mapping. That is a simple statement of given the open mapping theorem. So when the transformation of the graph T of G is open in B dash, whenever capital G is open sets is denoted by capital G and closed sets is denoted by capital F. That is our simple conversation. So capital T of G is open in B dash whenever G is open in capital B. G is open in B and that mapping is also open in B dash, image of the part. So prove that every point of T of G, every point of T of G is an interior point of T of G, because open means it is consisting neighborhood of points and interior points. So that's why given the every point of T of G, because G is open, every interior point of T of G is an interior point of T of G. So interior element is say small y, and there exists small x being the one of the element of capital G. So you must write the definition y equal to T of Tx. Now here x belongs to G. So G is open to open. So there exists an open sphere. What is the open sphere? S of x and r is contained are equal to G. Since what is the G dash of this path? S of xr can also be written as x plus SR, because x be the center of the fixed element. So that center is x plus this is SR. S suffix R we are taking. And image of the open sphere is sk dash, because here k is greater than 0. Sk dash contained are equal to T of SR. So y plus sk dash contained are equal to just you have to see and refer. Okay. Y plus sk dash contained are equal to y plus T of SR is contained are equal to T of G. Students, listen here. Please stay on the line. Okay. Y is an interior point of T of G. So S dash of y and k is contained are equal to T of G. Please stay on the line. Because there is no time to maybe tomorrow is the last class through the online session. Okay. So listen carefully. Once I have to repeat here. Y plus sk dash contained are equal to y plus, replacing sk dash means it is contained are equal to T of SR. So SR is also consisting of capital G. So yeah, enter this concept is S dash of y and k is contained are equal to T of G. So T of y, small y is an interior point of T of G here. T of G is open. So that is the simple proof in the examination. Just you have to see the statement is you must present the statement. Without statement, proof is not considered here. Okay. That is the open mapping theorem. This theorem is very important, and explain the one of the example. Okay, that open mapping theorem of T is onto is necessarily. Okay, if that continuous linear transformation is onto, then it is on. Then it is also the transformation is. The transformation is. Please say here open mapping. Okay. Now here the example of open mapping theorem is capital B equal to script R, and image of the Banach space is B dash equal to Cartesian product R cross R. That is order relation in between the system of real numbers. We are taking the Banach space. Here R, consider the set in the domain of the elements are real numbers, and Cartesian elements of the real numbers is we are taking in the image. So here T defined R2 R cross R. Here R represents that is the domain of the capital B, and R cross R is the Cartesian product of the elements. So that is B dash. So T of x equal to Cartesian element is that is also Cartesian elements. We are taking the x and 0. So T of x equal to x and 0. Here second coordinate is 0, because it this element is also referred radius of the part. Simply that is Tx. T of x means T suffix x or Cartesian product of x and 0, because radius is 0. for x belongs to capital R. So given the continuous linear transformation is, but it is T is linear continuous, but it is not onto. So express the define state open mapping theorem. Give example which is not an open mapping, or state and prove open mapping theorem. Give any suitable example which is not open mapping. Not open mapping means given the continuous linear transformation is not onto, that's why given the transformation is not open mapping. Okay, now this theorem is very important, students, and you have to refer another one, 7.4.4. This is the very simple theorem. Number of times is given in the short answers. That is 1-to-1 continuous linear transformation of one Banach space to another Banach space. B dash is a homeomorphism. If it is a 1-to-1 linear transformation, capital T of a Banach space onto itself, it is continuous, and inverse transformation is also a continuous. So that is the simple proof is T inverse whole inverse equal to T of G. That is T. T means T of G because G is open. So that's why inverse of the transformation is also a continuous. That is the simple concept. Students, listen carefully. This theorem is very important. Number of times is given. Now, in the recent paper, in the previous paper is given, short answer is S of XR equal to X plus SR. S of XR equal to X plus SR. How to prove this problem? Okay, S of XR means X be its center and R be its radius. We are taking the one of the element is Y. So distance between the X and Y is less than R. So S of XR being the one of the element is say Y be the an interior element. So if and only if distance between X and Y is less than R. So that's why norm Y minus X is less than R. Y minus X, say Y minus X by Z is there. So norm Z less than R means here Y equal to X plus Z. So if and only if norm Z less than R, here Z being the element of SR. So Y is also belongs to X plus Z means SR is here, replacing Z by SR. So Y belongs to X plus SR, and therefore S of X and R equal to X plus SR. And second one in the same manner, SR equal to, because here center at origin, SR means R of S1. These two problems are very important, students. Okay, and another one, the set of rational numbers Q is of first category in script R. This is also one of the example. And 7.5, 6.5, 7.6.6 in this unit. Now these two are very important. This is the end of this unit. See the another one, closed graph theorem. This theorem is also very important in the final examination. See and verify. This theorem is also tomorrow. We will explain the closed graph theorem and operators. Self-adjoint operator, normal operator, unitary operator. This is one of the another one important concept. See this unit 8th closed graph theorem is also very important in the final examination. Okay, please you must follow first of all what is the graph of linear transformation, and according to the definition you must explain the closed graph theorem. Okay, tomorrow we will explain. There is no doubt, because this theorem is very important. The gunshot theorems, there is no doubt. Entire the functional analysis, Horn-Banach theorem, open mapping theorem, closed graph theorem. These theorems are very important in the final examination. Without this one, without these theorems, you can't expect the functional analysis paper. Okay. Now, at the end of this session, we will explain on tomorrow's class closed graph theorem and applications, and some other operators are also here. Okay, those operators are here. The inner, what is the inner product space, and triangle inequality, Cauchy square inequality, and these are all very important and remaining units. Okay, especially in inner product space, very simple concept. All the students are presented perfect. That is not should not perfect in the examination, because before that inner product space, you must learn the inner product space. You must study the under UG level. Okay, UG level just means that is the linear algebra paper. See the linear algebra what definition of inner product space, Euclidean space, unitary space, and some other inequalities. And through the inequalities, triangle inequality, Cauchy-Squarge inequality, Bessel inequality. Those inequalities are very important, and especially here Rice-Fisher theorem and Parseval identity. Those theorems are also very important in the further session. Okay. You must refer closure graph theorem in the tomorrow's class. We will see and refer the these theorems tomorrow's session. Okay. Thank you one and all students. If you have any doubt, please contact through WhatsApp. Please note down my mobile number 9989476833. This is my number. Tomorrow's is the last session. If you have any doubt, please contact through WhatsApp for the subject point of view. Okay. 9989476833. This is my mobile number and WhatsApp number. Okay. Now, very simple paper, functional analysis paper is very simple. You must present through the subject. It is then automatically easily to achieve functional analysis relative to relevant to operator theory paper. Okay, don't forget this one. All the theorems are very important. Horn-Banach theorem and applications and lemmas, especially on the open mapping theorem. And before the open mapping theorem, we must define the one of the lemma is here, and some other problems are also referred in the open mapping theorem, especially in this session. Okay, tomorrow we will discuss the closure graph theorem, inner product space, and some other inequalities and operators. Okay, thank you one and all. Wish you all the best and wish you good luck. Okay, if you have any doubt, please contact as and personally through WhatsApp. Okay, for the subject point of view. Thank you one and all. Wish you all the best and wish you good luck.